Good afternoon. Thank you very much for the invitation. So thank you, Lucia, Matteo, all of you, Alessia, Maria, and so on. So I think I should be supposed to present something about our recent experimental results, but since we don't have recent experimental results, I will show you some old experimental results. And I will tell you something like a story of how we get to the point we are now and how we want to proceed after this. So it's a long journey in optics and photonics, which started a long time ago doing laser spectroscopy, then moved to ultrafast highly nonlinear optics and passed through quantum optics. And the final, the state where we are now and where we want to go in the future is this quantum light scattering that I will describe to you better in the next slides. So I can start with a long time ago, and those were the good old days of laser spectroscopy. And that was the time when I did spectroscopy, but the way it was meant to be. So with continuous wave lasers, very stable in frequency, very narrow bandwidth, and so on. So we measure absolute frequencies, line widths, line shapes, and so on as a function of pressure, temperature, and whatever. And in particular, I was working with Pittsburgh CO2 lasers, and we beat them together to generate a far infrared, so terahertz radiation. And so we perform a terahertz spectroscopy with these very narrow bandwidth lasers, tunable, and extremely so. And that was the case during all my PhD, essentially. At the end of my PhD, I switched suddenly to ultrafast lasers. There was a new laser system in the lab, and I was in charge of that kind of laser. And so, I had to change completely perspective, and I had to say, well, maybe I have to say farewell to spectroscopy. Because we are, of course, with very short pulses, we have broad bandwidths, so you don't expect to do high resolution spectroscopy with them. But, on the contrary, I was lucky, because at that time, there was this guy, Tadeusz, who was working in Florence, was teaching at the University in Florence, and we started playing together in the lab with these ultrafast lasers. And so we started to use, instead of just single pulses with spectroscopy, we started to use pairs of pulses delayed in time. And so we just use a very simple microscope interferometer. And by sending pairs of pulses delayed in time on the sample, and by scanning the delay, what we got was a sort of Ramsey signal. Or in other terms, you can think of these two pulses as having a sinusoidally modulated spectrum, which changes modulation as a function of the delay between pulses. And it is now this modulation which gives the spectral resolution that you can achieve. So by using this, we demonstrated essentially that we could perform indeed high resolution spectroscopy with very short pulses. And moreover, we could use also the high peak intensities, which is characteristic of the ultra short pulses, to drive the high nonlinear effects. Okay? So the next step, while we were thinking of this, was why don't we go further? So instead of using just two pulses, we can use trains of pulses. And by just using the bandwidth of the short pulses, why don't we increase the bandwidth of these pulses? So the natural idea was to use trains of laser pulses, like coming from the model laser, and maybe enlarge their spectrum by means of some nonlinear process. So the idea was to use a supercontinuous generation. And if this process was coherent, then we would have created this broadband combo of narrow spectral lines, which is what is called now a frequency column. But at that time, when we were thinking about this, this process of supercontinuous generation was really believed to be extremely messy and completely incoherent. So what we did was to try to do an experiment, a very simple experiment to test this. So we used the microsync interferometer again. We slightly misaligned the two arms of the interferometer so that we could focus the two of these pulses, pulses into different positions in this transferring material, so that we could generate two supercontinuous pulses out of them. And with very simple system, we saw very nice interface stages with far field, which meant that this process was not incoherent at all. It was not chaotic. It was not trace coherence by doing this. And so this kind of experiment was possible. And so these are really pictures we took in the lab at that time. And this picture appeared a few years later in Nobel Prize speech by Ted Einstein in 2005. What else could we do using this kind of technique? At that time, I was also using these ultra-short pulses to generate high-order harmonics. And this is what Caterina Bozzi told you yesterday. And we start from infrared pulses and we can generate down deep into the extreme ultraviolet of soft X-rays. So, well, we thought, why don't we use the same technique? So instead of using single pulse, we use pairs of time-delayed pulses to perform spectroscopy in the extreme ultraviolet with high spectral resolution. So again, the idea could be, we start with high-order harmonic generation, we split single harmonic pulses into two time-delayed, and we send them on sample. The problem is that you cannot do, at least, we couldn't do it that at the time, but I think it's still quite difficult to perform, to build a Michelson interferometer in extreme ultraviolet. So what we could do instead was to exchange these two steps. So first, generate a time-delayed pulses, and then hope to generate two time-delayed phase-coherent extreme ultraviolet pulses. But once again, this was was not so sure that we would have preserved the coherence between these two. So we did another very simple experiment, exactly the same as before. So we solved usual Michelson interferometer. We start from two phase-locked pulses, and we generated two harmonic pulses in two different positions in the gas chamber. So we generate two harmonic pulses now, and we check for their relative coherence by looking at interference fringes in the far field. And once again, so very nice interference fringes with some peculiar spatial and temporal distributions. And so immediately by looking at this, we saw that this kind of scheme was best possible. And indeed, we were able to do some run-safe spectroscopy in the extreme ultraviolet a few years later. This scheme can be used to do interferometry in the extreme ultraviolet. And this also, by looking at how these fringes behave, you can get information about the trajectories, electronic trajectories, which are responsible for the generation of harmonics. And by playing with this, with them, so for example, just by using an iris, which selects just this central part of the vision, it was possible to generate trains of second pulses. And once again, this picture that we took in the lab in Florence appeared 2 years ago in the Nobel Prize lecture by Hanjude in Stockholm. Okay, so everything was good. And it was around the end of the 90s. And again, suddenly I had to switch to something completely different. So I switched, the beginning from continuous wave lasers to fast lasers, from terahertz to extreme ultraviolet. And now I switched again from ultra-high intensities to single photons. So this was the time when a new laboratory started at the National Institute of Optics. And I was in charge of that. So we had to do optics at that point. And it took us some time. And after a while, we set up an experiments to generate single photons from, again, ultra-short laser pulses. So the idea, the scheme is a rather standard one now, which is based on a spontaneous parametric down conversion. So we start from modular laser with frequency down the emission of the pulse emission from laser. We use this as a pump for spontaneous parametric down conversion, and maybe it works. Yes. And of course, you know that sometimes you get with one of these spontaneous down conversion process, you generate pairs of photons, and you use one of them as a herald to announce the presence of the other photon in the signal mode here. Okay. So whenever we see a click in this detector, we know that there is a single photon traveling in a very well-defined spatial, spectral, temporal polarization mode towards this detector. And this detector is a homodynamic detector. So the idea, it works by mixing the signal that we want to measure with the local oscillator pulse, which comes from the same laser. This is just an intense coherent pulse, which serves as a reference. So we mix it on a bit splitter, and we take the two outputs, and we measure them with proportional photodiodes. And by taking the difference of these two signals, this difference is proportional to the quadrature, to a given quadrature of this field here, at the phase which is given by the phase of local spectrum. Okay, so we can do this and just acquire this data when there is a click from this detector. So it's a heralded generation and acquisition method. And once you do this, so you acquire a lot of this quality of data. You can do this as a function of this relative phase, and you can use this data to perform tomographic reconstruction. So we can essentially know everything about our unknown state here. So this was a single photon. You can either reconstruct the Wigner function or the density matrix, and so on. And so after a few years, we were at this point. We could generate single photons. And well, okay, so why don't we use now these single photons to again try to perform some spectroscopy? The problem is that okay, with these photons, they are extremely broadband. So using this normally picosecond or femtosecond lasers we are using to generate single photons. Also, our single photons are at this sort of broad bandwidth of the order of terahertz, and so there is no hope to have a sufficient absorption of these photons by normal atomic means, which have megahertz or gigahertz line widths. Okay. Nevertheless, what you may expect is that our single photons passing through a dense resonant medium can get, say, modulated somehow, not absorbed, but reshaped. And this is something that you know also from semi-classical optics. If you interact a short pulse with a resonant atomic medium, what you get is some, you have the area theorem holds and tells you how the envelope of your of electric field of your pulse modifies propagation. So in some particular cases, you can form these so-called zero area pulses, which is a sort of sequence of the both nodes in the envelope of your pulse as it propagates. So we wonder whether this is really working at the level of single photons. And so we set up an experiment to test this. So again, this is the scheme that I showed you before to generate our single photons. Now we put the rubidium cell here in the path of our single photons. And what we expect is that these single photons are now modulated in time. If you use balance on line detection to detect your states, you have to know that this is only sensitive to the part of the state that you want to measure, which is mode matched to the local oscillator shape. Okay, so if you use our, let's say, original local oscillator pulses coming directly from the laser to measure these single photons, you would see nothing, essentially, because they don't match at all. So what we have to do is to introduce some pulse shaping, where we can write the expected, let's say, shape for the deformation of pulse that we expect. And if we do this, we are indeed able to really measure these single photons with the clear negativity of the Wigner function, which tells you that in this process, the single photons you send single photons in, and you get single photons out without absorption. So we are still pure single photons, but we are able to change their spectral temporal shape. Okay, so you can do this in this very passive way, just traveling through an atomic medium, but you can try to do it also in some active way. So to change the shape of your single photons in some active way. And one way to do it, a very simple one that we used for our first experiment, was to introduce some shaping of the pump of the pump pulses that we use to generate signal conversion. Okay, and the simple way to do this is again to use a microsynthrometer, an unbalanced microsynthrometer, such that, for example, we have this sinusoidal modulation of the spectrum. So if you put a minimum of this modulation in correspondence to the peak of the pump spectrum, what you get is essentially a pump spectrum which has a double peak in frequency. Okay, and so you can use this pump, now shaped pump, to generate single photons, which inherit the shape of the spectral shape of the pump. So, well, I don't have time to tell you how, but we can measure essentially the spectral shape of our single photons, and we can essentially demonstrate that we can just like essentially generate a single photon which is in a coherent superposition of two different colors. Okay, so if you consider this as two different, let's say, base states, this is a sort of a single photon spectral. And so this is a very, let's say, very simple way, very naive way of generating, of changing the spectrotemporal shape of your single photons. In principle, I mean, you can make this delay here longer so that you have a finer modulation of this. And so you may have a spectral qubit, a single photon spectral qubit, which in principle you can tune and encode information also just in the spectral profile of your single photon. So this is for, let's say, sculpting. Go back to the title of my talk, sculpting the shape of a single photon. What else can we do? We can also sculpt not just the shape of state of light, but the state of light itself. And this is something that we started to do again a long time ago. And so what we did was to implement these very basic operations of photon addition and photon subtraction. So these are really the basic ADAC and DAC operators that you learn in the quantum mechanics courses. And you can implement them in an experimental way. For example, the photon addition with a simple modification of the scheme that you use to generate the error with simple photons. In that case, you just had spontaneous parametric quantum inversion. In this case, you have stimulated parametric inversion. So you inject the signal mode of your crystal with some arbitrary state of light. And let me go back so I can show you again the movie. And so you see that whenever this one clicks, whenever you have the down conversion process, you know that you have added exactly a single photon on the state which was injected in this signal mode. So within some approximation, some constraints, this is a faithful implementation of the ADAC operator. And on the other hand, you can also implement the photon subtraction operator, this A operation, by just using a beam splitter of low reflectivity and looking at the click on this detector. So whenever you see click here, again, within some approximation, you can, what you get here is just the A applied to the input state. Okay, so these are very basic tricks or Lego blocks that you can use now to really engineer the state of light. And so we did this for many different combinations. And some particular examples are, say, this one that we use to test computational relations. So what we can do here, you see, we first put a photon subtraction and then a photon addition, and then another photon subtraction. And if you see two of these clicking, it means, for example, in this case, it means that first you had a photon addition, then a photon subtraction. But if these two click, it means that you had the reverse sequence of operations. So you can implement the ADAC and the ADAC-A, and so you can apply them to the same input state here and look at the final results. If they're different, it means that the A and the ADAC do not commute, which is something that you learned in the first year in quantum mechanics. You can also try to implement the full computation relation, so with this minus here, and this means that you have to implement a coherent superposition of operator sequences. And experimentally, we simply do it. I don't know if you can see it, but anyway, there is a slight change here. We mix these reflected arms for two beam splitters. We mix them on another 50% beam splitter here, and we just look after the beam splitter. So when we see a click here and a click here, we know that there was a photon addition taking place, and we know that there was a one photon subtraction taking place, but we don't know if it was before or after the photon addition. And you can carefully, I don't see it, yeah, it should be here, carefully adjust the relative phase here. There's a phase shifter. So you can really implement this minus in this expression, and you can really implement the commutator operator. So you do all this crazy stuff, and just to find out that the input state just appears identical as the output state, because this is really identical operation. So we did a lot of stuff to play with this very basic tools, basic operations in quantum optics. But these are all single mode operations. So we are always traveling on the single, well-defined wave packet modes, which are traveling at the speed of light, of course. Can we do also something more? Can we operate on multiple modes at the same time? And yes, we can do it. So we can just modify a little bit our scheme. So this is exactly the same as I showed you before. Just the only difference is that instead of going directly to the detector to generate a single photon, to generate a single photon in a well-defined mode, we go to this heralding detector passing through a Mach-Zehnder interferometer. And this Mach-Zehnder interferometer is unbalanced, and the time difference between the two arms of the interferometer is exactly equal to the time difference between the two successive pulses coming from our laser. Okay, so when you see a click in this detector now, you don't know if it arrived from the short path here or from the long path here. So you don't know at which time you added the single photon. So if you start from two, let's say, two arbitrary input states here, which are separated by tau, this time difference, and you see a click here, you know that you added a single photon to one of these two, but you don't know which one. And by just doing this coherent, delocalized photon addition over two different modes, you entangle them. Okay, and then you can use your. This is a very convenient scheme working with these temporal modes because you don't have to double your apparatus for each additional mode. And you just, in principle, can use more pulses and more delay lines here, and use the same model detector because you can just multiplex in time the measurements. And so this is an easy way to really generate multi-mode entanglement. So we can do this in principle with arbitrary states here. We did the first experiments a long time ago, which just started from vacuum, and it's okay. So, and if you start from vacuum, you see a click here. You generated a single photon somewhere, either here or there, but you have a linear superposition of these two possibilities. So you generate this 1001 state, which is a path entangled state. And this was also with when Milena was working in Florence with me. But then you can also try to do something more interesting. So instead of having just two vacuum states here, you can have the one vacuum state and one coherent state, for example. And if you do this, I don't have time to explain, you generate another entangled state, which is now, well, we call them an hybrid entangled state because it entangles two modes, one which is encoded in discrete variables, 1, 0, and the other one which is encoded in continuous variables, alpha and minus alpha, which can in principle be used for interfacing, for example, quantum information networks which work with different components. And then recently what we did was to move on, and instead of having 0, 0 or 0 alpha, we have two coherent states in these two modes here. And what happens if you apply this linear superposition of photon additions on these two modes is the following. Okay, so if you just write it down, you find out that it's made of two parts. One which is always entangled. This is just a displaced version of this 1001 state. So this is entangled. And another part which is separable is just your initial two coherent states, which are just a completely separable state. And the ratio between these two contributions is given by this phase factor phi. So in particular, if pi is equal to pi, this is -1, this term just goes down, where it goes away. And so you are left only with an entangled part. And this entanglement, in principle, stays constant, independent of the values of alpha. So this is a way to entangle even microscopic states in light, just by sharing a single photon between them. Okay, so in principle, you start from two intense coherent pulses of laser light just to share a single photon between them and get entanglement. So we were able to demonstrate that entanglement indeed persists up to coherent pulses, which have on average about 60 photons each. This is not independent of alpha. So this is the negativity of partial transposes. It's measurement of entanglement anyway. And so ideally it should stay constant, 1, but you see it goes down. And the problem is that this is a very fragile entanglement is very fragile, this kind of state. And this is due to the fact that as soon as this phase just fluctuates around pi, you immediately this separable part appears, and then the entanglement quickly dies. What is nice is that you can use this fragility. So if you redraw the experiment, I mean, it's the same scheme as I showed you before, but now you can separate this, let's say, heralding part from the rest of the setup. So maybe you can put this heralding part far away, and you can use actually the fragility of the entanglement of these two modes here as a measure of tiny phase fluctuations which take place somewhere far away. Okay, and so what we did this, and well, measuring the entanglement is not so easy. Yeah, okay, it's not so straightforward. It takes full amount of state, so it's not very convenient. So we found that instead of just measuring the difference of the peak quadratures in these two modes is enough to get an observable which is strongly dependent on this space here. Okay, and so we did the theory, we did measurements, and we found that indeed we have a phase sensitivity, a remote phase sensitivity, which scales essentially proportional to the intensity of one of these two planar pulses here, which essentially, I mean, if you put a sample here, these pulses never interacted with the sample. So you have a sensitivity which scales with pulses, with the intensity of pulses which never interacted with the sample. So which was quite interesting. Last nice property of this kind of states is this correlation. So if you think about the initial two planar states in these two modes, now I drew them here as two separate spatial modes, but we are always working with two temporal modes. Okay, but it's just because it's a nice picture. And so if you just look at the original two planar states and you plot the joint photodynamic probability distribution, so the probability of measuring any photons in one of the two pulses is independent of the probability of measuring another number of photons in the second mode. If you perform this delocalized photon addition, you get something which is quite different. So you take a whole valley here along the diagonal, which tells you that whenever, I mean, if you do this, whenever you measure the number of photons in this mode here, you are sure that you will never measure the same number of photons in the other. So this is sort of complementary to what you do with the two-mode split slide, where you have perfect correlation in the number of photons in the two modes. You have perfect discorrelation. Whenever you see a number of photons in one mode, you see something different in the other one. Okay, so these are experimental results, and you see that, okay, of course you have some inefficiencies, so you never really go down to zero along the diagonal, but it works. And in principle, this could be used for, well, it's nice to see, but this would be used also for some particular quantum information tasks, like security voting and so on. And in principle, well, the first time this was, okay, this kind of scheme could be used for solving a classical problem of playing poker on the phone. Because differently from playing chess on the phone, where all the information is available to all the partners, if you want to play poker on the phone, you have to really trust your opponents, and you have to trust the card dealer, because I mean, you cannot. And if you distribute this kind of states to the two players, then you're intrinsically certain that they get different cards, random and different. Okay. Okay, this is all. And so this is what I wanted to say. So we are able to essentially manipulate the state of light photon by photon by adding and subtracting photons and performing sequences of superposition of these operations. On the other side, we are able to do this single photon mode morphing. So at the moment, we have only done this with single photons, but we are able to change the spectral temporal shape of the mode which contains single photons. So what we want to do in the future is to really try to merge these two things, and so perform arbitrary quantum state engineering over modes of arbitrary shape. So to have a full control of the shape and the mode and the state of the quantum light. So well, it was a long story. I showed you extreme changes from high intensity to single photons, from stable continuous wave lasers to ultrafast laser, from terahertz to extreme ultraviolet, and it took a lot of people to lot of really great people to work with. And so I'm grateful to all of them and to many other people. I don't show you my group now because it's only made of me and just a young postdoc who just arrived 2 months ago. So I mean, I don't have pictures at the moment. And okay, this is all. Thank you very much.